All right, ladies and gentlemen, welcome back to AP Chemistry with Mr. Kenton. Thank you so much for joining me today. I'm excited about today's lesson of looking at photoelectron spectroscopy because photoelectron spectroscopy is a really neat tool that has given chemists a lot of information about the structure of the atom and specifically the energies of the orbitals that we talked about when we started looking at electron configuration. So I'm excited to share this with you. Let's go ahead and dive right in. This is going to be fun. Now, photoelectron spectroscopy, commonly referred to as PES, is a process that utilizes the photoelectric effect to measure the kinetic energy of an electron in order to measure the energy of the orbitals from which the electrons are lost. Now, I'm going to take a step back for a second and just kind of remind us, remember, photoelectric effect is this idea that when you shine light on the surface of a metal or a substance, that it's going to eject photons off of the surface if they've been hit with enough energy. Now, we also talked about how we could increase the energy at which they're being kicked off by using light that has a higher energy content, right? So using UV light, X-rays, or even gamma rays would cause the increase in kinetic energy. Now, to look at the change in energy here, which we're going to call the binding energy, delta E binding energy, is going to be equal to h nu, which is from Planck's constant. So Planck's constant times the frequency minus the kinetic energy of the electron that's being lost. So that's how we're actually going to calculate binding energy. And so when we look at this, if we analyze the kinetic energy and we know the energy of the photon that's being given off, then we can determine this binding energy, which is the energy that is keeping the electron within its orbital. This is what explains why the electrons don't just simply fall into the nucleus and are attracted to the protons. They have this binding energy that's keeping them in place. Excuse me. Now, I would encourage you, go take a look at that particular website. It gives you some more information about photoelectron spectroscopy. Might kind of pique your curiosity, so you could look at all the different things that people do with PES. Pardon me for taking a water break. Now, here is the machine that you're going to run PES through. Now, it looks really complicated, right? Like there's lots of chambers, there's lots of cores, there's lots of wires, there's lots of, it looks like there's a lot of stuff going on there. Now, if we just break it down, simply what it's doing, we've got these two graphics over here. And so one part is going to be your light source or your photon source. So here we've got our UV or X-ray source. I actually like this picture down here, so I'm going to focus on this one. So you've got your photon source. It's going to kick out UV or X-ray light. So you shine your light on it, h nu. You've got your sample, which is going to be placed in a UHV chamber, which means ultra-high vacuum. And in that ultra-high vacuum chamber, it's going to allow for the sample to be pure, and it's going to allow for those electrons to move exactly where we need them to. So we shine our light source on our sample, electrons are given off, they travel upward, they get captured, and they move into the energy analyzer. As it moves into the energy analyzer, it's going to produce a readout that's going to give the person running the machine a readout to be able to read the energies of the different electrons that were removed. It's pretty neat. Now, don't get too caught up in all this. You're not going to have to draw this on the AP exam. You're not going to have to explain the machine itself, but you have to understand what PES does. And so that's why I wanted us to take a look at the piece of equipment that chemists use. Now, there are two types of PES because they're going to give us different pieces of information. The first type of PES is XPS, X-ray photoelectron spectroscopy. Now, X-ray photoelectron spectroscopy uses X-rays. Now, the X-rays are going to have an energy between 200 and 2,000 electron volts. And so that radiation is going to be used to examine the core electrons, those inner electrons in a given sample, in a given atom. The second type of photoelectron spectroscopy is ultraviolet photoelectron spectroscopy, UPS. Okay. Now, again, using vacuum ultraviolet light, that gives off an energy between 10 and 45 electron volts. That radiation is going to allow the person studying this sample to examine specifically the valence electrons for a given substance. So keep in mind, X-ray photoelectron spectroscopy deals with our core electrons. That's why it requires more energy to remove them, right? Think of how Coulomb's law plays into effect here. Whereas with UPS, deals with those valence electrons, which are a lot easier to remove, so it requires an energy source that has less energy. Now, what exactly do you get when your photoelectron spectroscopy is done? What kind of readout? What does it produce? Well, you ask and you shall receive. Here we go. So here are your examples of what you would get for a PES if you were to run it through that machine. Now, I do want to draw your attention to the fact that both of these samples are complex. These are compounds that have been run, and so that's why you've got these differing peaks here. You've got this weird complex that's here, and even over here, this is aluminum oxide, and you've also got rhodium that's attached to that aluminum oxide as well. Now, that's great and all. You got these different peaks, but what I want to draw you to, the energy associated with the particular electrons is on the x-axis. That's true on both of these diagrams. And then the other thing that you're going to notice is that there are these little tick marks over here. Those are going to correspond to the electrons, the number of electrons that are there. Now, when you start to look at that, you might be getting overwhelmed. You might think, Mr. Kenton, I have no idea what I'm looking at. It just looks like a bunch of graphs, and there's some of these peaks. I don't know what this means. Well, the good news is AP is kind of nice to you guys, and the type of samples you're going to have to examine looks something like this. It's a lot simpler. Okay. Now, as we look at this particular diagram, I want you to notice, again, the x and y axes are the same. The x-axis is showing us the binding energy in megajoules per mole, and the x and the y-axis is our relative number of electrons. Now, when we look at this, this is a taller peak than this one. This is telling us there are 2 electrons here, 1 electron here, so that's a total of 3. So, if this is what we got from our sample, if this is what our PS computer analyzed, what element is this? Hopefully you guessed lithium, because it's got 3 electrons. Now, a question for you guys to consider is, why are these electrons over here, why do they have such a higher binding energy compared to this 1 electron over here? Well, hopefully you recognize these have to be core electrons. This would correspond to the 1s orbital of lithium, whereas this peak over here corresponds to the 2s orbital for lithium. Now, as you get into more complicated diagrams, each peak is going to represent a specific subshell within that particular atom. So counting the number of peaks will help you determine how many subshells your particular atom has. Now, again, looking at the graph, the y-axis gives you the number of electrons, and the x-axis is giving us the energy of the electron, or the binding energy. Now, I will note, binding energy is given here in megajoules per mole. You could see kilojoules per mole. You could see electron volts. But that's what you're more than likely going to see. Now, here are some examples that I want you guys to tackle on your own. So, again, when you're watching these videos, when we get to something like this, pause the video, analyze the information there, and come up with your answers. And so, as you do that, I also want you to consider not only what elements these are, but what would be the electron configuration for those elements? What do these peaks, what sublevels do they correspond to? So now that you have that question, pause the video, identify the identities of the elements, and identify the sublevels that the electrons are residing in. Now, hopefully you paused the video, you took the time to write out your responses, and hopefully you've come up with something. So if we look at this one on the left, so we've got 2, 4, 8 electrons total. So that means the identity of my substance is oxygen. It's got 8 electrons. Now, the other thing that we want to figure out is, what are these peaks? What do they correspond to? Well, something that I'm going to do is I'm going to look for my highest energy peaks first, because if I find those highest energy peaks, I know where my core electrons are starting. I know where my closest electrons are, which is going to give me my 1s sublevel. So this peak right here at 52.6 megajoules per mole, that's going to correspond to the 1s sublevel of this particular substance, right? Oxygen. Now, as I come down here, I move into its valence shell. I've got my 2s orbital, because its binding energy is at 3.04, because it's a little bit closer to the nucleus, so it has a slightly higher binding energy. And then my 4p electrons are at that 1.31 peak, because they're going to have slightly less binding energy, because they're a little bit farther from the nucleus. Now over here, for yellow, so we're going to have 2, 4, 10, 12, 13. All right, I don't have a periodic table in front of me. I think this is aluminum. You can call me out in class if I got it wrong, but check that, 13 electrons, that's aluminum. Now, each of the peaks, again, we find the highest energy peak, that's going to be our 1s sublevel. So this is our 1s, this is our 2s, this is our 2p, this is our 3s, and this is our 3p. So that's the electron configuration for aluminum. Pretty straightforward, I think. Now, the other thing that we want to look at is, we're going to focus on this one over here, because this isn't really comparing much of anything. When we look over here, we notice that we have carbon in blue, we have nitrogen that's in pink. Okay, now when we look at these particular peaks, we've got, this would be the 1s sublevel for nitrogen, so 1s sublevel for carbon. Now notice that there is a shift. There's a shift there. Now, I want you to think about what could be causing there to be a shift in the binding energies of the 1s sublevels of carbon and nitrogen respectively. Well, hopefully, when you looked at that, hopefully you're noticing that it would be the fact that the effective nuclear charge for nitrogen is slightly greater than that for carbon, so it's going to hold on to its core electrons more tightly. Now, we see the same thing happen at the 2s sublevel, right? There's a shift. Nitrogen's holding on slightly more tightly to its electrons than carbon is. And then, when you transition to the 2p, you've got the 2p sublevel there. Now, these are pretty basic, but just understanding what's going to cause those shifts, notice how it goes back to Coulomb's law. I mentioned it's going to be pretty important, so it's good that we went over that first. Well, ladies and gentlemen, that's all I've got for you guys with photoelectron spectroscopy. This is a really cool technique. I'm glad I got the opportunity to share it with you. I hope that makes sense. If you do have any questions, please let me know in class. I'd be more than happy to help you. Thank you guys so much, and I'll see you again soon.